Okay, so from here we're just going to consider different forms or different representations for the velocity or the acceleration, depending on what's been given in terms of the other variable. So normally everything is in terms of t, dv dt, x dt, etc. Well, maybe this time our velocity might be given in terms of x, or the acceleration might be in terms of v, or acceleration in terms of x. So you just got to be careful what you're integrating with respect to. And moving forward, we'll use different representations for the acceleration to help us get the desired outcome. All right, so if we have a quick look in here, velocity of a particle moving in a straight line is inversely proportional to its position. So the velocity is inversely proportional. So if it was proportional, it's just y equals mx plus c. Inverse, 1 on x. So in other words, what we're saying is the velocity is inversely proportional to its position. So v is equal to some kx. Okay. Now we don't often get the information given to us in a statement like that. Often they'll give us velocity is equal to some k on x. Okay. So clearly again, velocity itself is, we want to get the position in terms of t. So we want x and t to be our variables. So velocity is dx dt. So we're just going to have to swing things around a little bit, aren't we? dt on dx would be x on k, and then we're going to integrate with respect to x. So we get t is 1 on kx squared plus c, an initial condition in terms of k. Substitute everything back in, and we've got t equals. So then we have to rearrange or transpose to get x equals, don't we? So we end up with an x squared is equal to 3t plus 1. So x is equal to, in reality, the plus or minus the square root of 3t plus 1. But since from my initial condition at t equal to 0, x was greater than 0, well, it must be the positive square root. All right, so there's my relationship now for x in terms of t. Then the next part of that goes on to talk about find an expression for the particle's velocity. So in other words, I need v, which is dx dt. So if I've got x equals, I'm going to integrate that expression with respect to t to get v in terms of t. Okay, so just using our integrate. We've got x is equal to and dx dt. So differentiate that with respect to t. Sorry. Yeah, and so then we'll end up with our, minus a half at the front, take 1 off the power, etc., etc. Okay. What about the next one? The next one's similar in that we've got our key variables, but they're a little bit different in terms of how they've been related to each other. So again, we've got our acceleration here in terms of v. So acceleration, dv dt, okay, is equal to some negative k 50 minus v. Okay. So again, flip it upside down and integrate. So we're going to integrate everything with respect to v. We get our log function, our 1 on k. I'll go through our rearranging process. So v is equal to some negative a, or a, because a is going to be a constant, plus 50. Put an initial condition in for t equal to 0. My velocity is 25. Rearrange that and I'll get a is equal to 25. So I've got a rule for my velocity now in terms of t, and then, which is what we were after, and hence sketch a velocity time graph. So even though we don't know that constant, we can still work around it. We know it's an e to the x graph that's been reflected about the x-axis, and it's been moved up 50 units. So t equal to 0, we've got our initial velocity of 25 meters per second. And then if we transpose and solve for where v is equal to 0, we'll get t is some 1 on k natural log of 2. So there's our graph. Yeah, so it's just a case of keeping note, taking a note of the variables that you have and the final answer, what it needs to be in terms of.